Now that we understand the motions of why it is that the planets are orbiting in the same direction in roughly the same plane, now we need to explain why there are two planetary types. To be able to explain why there are two planetary types, we have to go back to what everything is made of. If you remember previously, we've mentioned that the universe is pretty much hydrogen and helium. 98% of everything is hydrogen and helium, with about 74% hydrogen, 24% helium, and all other elements make up only about 2%. Now, do you remember where this 2% comes from? This 2% comes from stars. The hydrogen and helium, all of the hydrogen and most of the helium in the universe, comes from the Big Bang. And then the rest of everything comes from stars, as stars age, evolve, and eventually die. Now, something else we need to remember is the temperatures throughout the disk. So remember, the center of the disk is very, very hot, and as we go from the center out towards the edge, it cools off. Well, because we have this difference in temperature, this means that different materials are going to be able to condense. What we mean by condense is go into a solid state, actually begin forming solid particles. So rock and metal are able to condense at very high temperature. Think about the melting point of rock and metal. This stuff is really, really hot when it finally melts. So it's going to be able to form into solid particles even at very high temperatures. What this means is rock and metal are going to be able to form everywhere throughout the disk. Whether it's hot or cold, we're going to be able to form rocky particles. Ices, on the other hand, only form in cool conditions, which means near the protosun, where it is the hottest, we're not going to be able to form icy particles. So ices are only going to form out in the outer solar system, at a good distance away from the protosun. So in towards the center, we get rock and metal. Out towards the edge, we get rock, metal, and ices. Now, something that I want to point out is that hydrogen and helium will never condense within the nebula. This stuff is always going to remain as a gas. So the distance away from the protosun, where it gets cold enough to finally begin forming ices, we refer to this as the frost line. So inside the frost line, we only get rock and metal. Outside the frost line, we get rock, metal, and ices. Now, as these pieces begin to condense, they're going to start forming small flakes. For me, what I often think about is kind of how snowflakes form. So up in the clouds, it gets cold, which allows the water vapor to actually freeze into ice crystals, forming snowflakes. So we start forming these flakes of material everywhere throughout the disk. Well, occasionally, these flakes are going to bump into each other, and if they're going slowly, they'll actually stick and grow into larger flakes. So if you've ever been in a snowstorm with those big, giant monster flakes, if you actually look at those, it's not one giant snowflake, it's actually a whole bunch of small ones that have stuck together. This is the process of accretion. Okay, so we have this process of accretion where the small things are sticking together, growing larger and larger. Well, over time, these pieces, as they're getting bigger, are going to grow large enough that gravity is going to be able to start pulling them together. At this point, where they're big enough that gravity helps them accrete, then we refer to these objects as planetesimals, and they're about the size of modern-day asteroids. So they're getting pretty big. So at one point in the early solar system, we had hundreds of thousands to millions of planetesimals all orbiting around the sun. Now, there were so many, and they're all pulling on each other through gravity, so they did not have any stable orbits, which means they're going to continue to slam together, growing larger and larger. Now, over time, these will continue to accrete until we have a few dozen of what we refer to as protoplanets. These are objects that are closer in size to modern-day Mercury or the Moon or possibly even Mars. But there's still enough of them that are pulling on each other gravitationally that they still have some random chaotic orbits until they continue to slam into each other, and finally we're left with just a few planets that are now nicely separated and have now nice, stable, nearly circular orbits. We actually have evidence of this process of condensation and accretion from meteorites. A meteorite is a lump of rock from space. So most meteorites formed through the same processes as the planets, they just didn't get swept up, or at least not initially. In this case, what we're looking at in the picture is a type of meteorite known as a chondrite, because it is made up of all of these smaller pieces called chondrules. Okay, this sort of meteorite actually shows this process of accretion, though it's formed from smaller bits that have come together. All right, here's another question for you. What could condense in the outer solar system? A, metal and rock, B, water and methane, C, hydrogen and helium, or D, both A and B. So metal and rock, water and methane. Go ahead and think about it, and we'll discuss in just a bit. So in the outer solar system, it is going to be cold. Metal and rock are going to be able to form not just at high temperatures, but at any temperature less than high temperatures. So metal and rock form everywhere throughout the disk, no matter what. That's actually not true. Really, really close to the protosun, they're not going to form. But you have to get really close to the protosun for that to be the case. Water and methane are only going to be able to condense, turn into ices, beyond the frost line, so as part of the outer solar system. Hydrogen and helium never condense into a solid in the conditions of the solar nebula, which means that in the outer solar system we'll get metal and rock, water and methane, so the correct answer is D, both A and B. So in the outer solar system, we have rock, metal, and ices. What this means is we now have more material that we can use to form planets, and because there's more material, this means we can form bigger planets. So the Jovian planets likely began to form in the same way as the terrestrial, through condensation and accretion. But because of that extra mass from the ices, they got so large they were able to start pulling in the hydrogen and helium gas from the solar nebula. So they pull in hydrogen and helium, which means they become more massive, so they're able to hold on to more hydrogen and helium, which means they're more massive, and so on. So they continue to grow, pulling in the mass, pulling in the hydrogen and helium gas from the nebula, until they turn into the giant Jovian planets that we have today. Now, as these Jovian planets form, because of how big they get, they actually begin forming a disk around themselves. So similar to how we have the protosun with the protoplanetary disk around it, we have the proto-Jovian planet with a proto-moon disk around it. So some of the Jovian moons actually formed through the same processes as the planets. They formed through condensation and accretion around the planet, just like the planets formed through condensation and accretion around the sun. Now, this also helps us explain where comets and asteroids come from. These are the debris that are left over that didn't get swept up into the rest of the solar system. If you remember, asteroids are made up of rocky and metallic material. This means they had to form in the inner solar system. Comets are made of rocky and icy material, which means they had to come from the outer solar system. But all of this stuff are the things that did not get swept up into the planets originally. Now, eventually, the protosun begins nuclear fusion in its core, which means it's going to begin having the solar wind, this constant flow of radiation and particles streaming out away from it. This is going to then push out the rest of the material that didn't form into large solid objects, or larger objects, I should say. So this then reveals the solar system as we see it today. In this image, we see a group of young stars that are currently in the process of pushing the material away. Now, we are still left with one problem. The Earth formed in the inner solar system. It is a terrestrial planet. But ices did not form in the inner solar system. And yet, we know that the Earth has lots and lots of water. Now, not huge amounts, but quite a lot. So, how did it get here? The current understanding, the current ideas, is that early on in the solar system, there's this time referred to as the period of heavy bombardment. During this time, a lot of material from the outer solar system actually came raining in to the inner solar system, bringing all of those ices with it. It is likely during this time of heavy bombardment that material from the outer solar system brought water to the Earth and the other terrestrial planets. The current thinking of why we have the period of heavy bombardment is actually because Jupiter moved. Something that we've learned, we'll talk about more later on, is that planets don't actually necessarily stay where they formed. We think that Jupiter actually early on was farther out, moved in, and actually got close to the asteroid belt, and then drifted back outward until its present location where we see it today. That drifting back and forth then disrupted the material, sending a lot of it falling into the inner solar system, bringing the water that we now have. All right, here's another question. Why are there asteroids and comets? A planet exploded due to chemical reactions in the core. B, these are leftovers from when the planets were accreting. C, they are evidence of interactions between two planetary systems colliding. Or D, it is the leftovers of a planet destroyed through intergalactic war. Go ahead and think about it, and we'll discuss in just a bit. All right, the correct answer is B. These are the leftovers. This is the stuff that did not get swept up when forming the planets. All right, here's another question for you to think about. How would the solar system be different now if the solar nebula had cooled with a temperature of half its actual value? So how would the solar system be if the protoplanetary disk was half the temperature that it actually was? A, Jovian planets would have formed closer to the sun. B, there would be no asteroids. C, there would be no comets. Or D, terrestrial planets would be larger. Go ahead and think about it, and we'll discuss in just a bit. All right, so if the entire thing was cooler, this means that that frost line, the distance where we're able to form ices, is going to move in closer towards the sun. Inside the frost line, we only have rock and metal, which means only terrestrial planets. Outside the frost line, we have rock, metal, and ices, which means that the planets are able to grow larger and actually begin trapping hydrogen and helium gas. So we begin forming Jovian planets beyond the frost line. So if the entire nebula was cooler, this means that the frost line had to be moved in a lot closer, so we'd expect Jovian planets to actually form closer to the sun. So the correct answer is A.